Some systems store a long history of rotations, but instead of keeping every tiny turn in one place, they can compress that history into coarser layers and later rebuild the finer motion when needed. This video explains a three-layer rotation memory model in which unit quaternions record turns, block products compress fine motion into coarse motion, a Markov current drives circulation between layers, and a closure check keeps the whole cycle geometrically consistent. The key idea is that memory is not only stored, but actively moved through a loop of fine, middle, and coarse scales. So the first step is to understand what kind of rotation object each layer stores. Each layer stores rotations using unit quaternions, which are four-number objects of length 1 that represent three-dimensional rotations without the gimbal lock problems that can occur with ordinary angle coordinates. A unit quaternion has a multiplicative inverse, so one rotation followed by the inverse rotation brings the system back to where it started. The model has an outer layer with 720 frames, a middle layer with 72 frames, and an inner layer with 10 frames, so the same rotation history is represented at fine, medium, and coarse scales. Instead of storing only the absolute rotation at each frame, the outer layer stores delta rotations, where each delta means the change from the previous rotation state to the current rotation state. Multiplying the deltas in chronological order reconstructs the full outer rotation history, because each intermediate state cancels with its inverse in the product. This cancellation is called telescaping, and it means that a product of consecutive delta rotations is exactly the net rotation across that whole block. To compress the outer layer into the middle layer, every 10 consecutive outer deltas are multiplied into one block rotation, turning 720 fine updates into 72 medium updates. The middle layer stores the inverse of each outer block rotation, so it acts like a counter rotation that compensates for torsional drift from the fine memory layer. The middle layer is then compressed into the inner layer, but 72 does not divide evenly into 10, so the blocks cannot all have the same size. The middle to inner compression uses variable blocks of 7 or 8 middle frames, and those blocks partition the 72 middle indices, so every middle frame is used exactly once. The order of multiplication matters during this compression because quaternion multiplication is associative but not commutative, meaning the grouping can be shifted safely, but the order of rotations cannot be swapped freely. The inner layer stores the coarsest equilibrium structure, so it keeps a compact version of the rotation history after the outer details and middle inverse corrections have been folded inward. To move information back upward, the model uses fractional powers of unit quaternions, where a rotation can be split into equal smaller rotations along the same rotational path. This interpolation is often called spherical linear interpolation, or SLIRP, which means moving smoothly between rotations on the unit quaternion sphere. If a unit quaternion has an angle inside the principal range from -pi to pi, then taking its 1/n power and applying that smaller rotation n times recovers the original rotation. That fact lets one coarse middle update be spread evenly across 10 outer frames, so a compressed rotation can be lifted back into a fine sequence without changing its net effect. The compression and reconstruction steps describe how rotation memory moves between scales, but the paper also treats the three layers themselves as states of a Markov chain. A Markov chain is a system that moves between states with fixed transition probabilities, and here the possible states are the outer 12-point gear, the middle 10-point gear, and the inner 8-point gear. For two states, the current from one state to another is the stationary probability of being in the first state times the transition chance to the second, minus the reverse flow. If the current around the cycle from outer to middle to inner and back to outer is positive, the memory is circulating in a preferred direction rather than merely diffusing back and forth reversibly. At stationarity, the total probability at each of the three layer states stays constant, so the amount of current entering and leaving each state must balance. Because three connected states form a single cycle, that balance forces the three edge currents around the loop to be the same current with the same sign. Therefore, the pump condition can be read as the positivity of one cycle current, which is the mathematical sign that detailed balance has been broken. Detailed balance is the reversible case, where every pairwise flow is exactly matched by its reverse flow, so breaking detailed balance is what makes the memory pump active rather than passive. The final consistency check is holonomy, which measures the net rotation left after going around a closed cycle of layer rotations. If the product of the inner net rotation, the middle net rotation, and the outer net rotation equals the identity rotation, the cycle closes perfectly. If that product is close to but not exactly the identity rotation, the leftover rotation is a small drift that must be measured and redistributed across the layers. The model measures this drift with the logarithm of the holonomy rotation, then applies small correcting rotations to the outer, middle, and inner deltas with weights that add to 1. After correction, each quaternion is renormalized, meaning it is divided by its own length so it stays on the unit quaternion sphere. The complete mechanism is therefore a multi-resolution quaternion delta chain with an inverse middle compensator, an active Markov circulation current, and a holonomy correction that keeps the rotation memory coherent across cycles.